Good morning. Today we're looking at 2017 AP Chems FRQ number 2. We're going to start with A. It says answer the following questions about the isomers fulminic acid and isocyanic acid. And it says two possible Lewis dot structures for fulminic acid, or HCNO, are shown below. Explain why the diagram on the left, which is this one, is better representation for the bonding in fulminic acid. Justify your response in terms of formal charges. And it tells you right off the bat that we need to be looking at formal charges. Formal charge, for those of you who have forgotten, is a way of measuring what the effective charge of a molecule is. Formal charge is the valence electrons of a neutral molecule minus electrons present in bonded molecule. You subtract the two of those, that would give you your formal charge. So let's take a moment here and really quick go through how many dots or valence electrons each of these would have. We'll start with hydrogen, then talk about carbon, then nitrogen, then oxygen. Okay, starting with the left, hydrogen has 1 dot. Carbon, if we go look at it on the periodic table, has 4. Nitrogen has 5. Oxygen has 6. So any deviation from that will tell us our formal charge. For instance, we look at hydrogen. When you count formal charges, you count electrons in lone pairs, and then you count bonds. And you count the number of bonds, or half the electrons in bonds, whatever you prefer. So I have 1 bond, so it's 1 from there. So 1 neutrally, normally, and 1 bond gives me 0 electrons. A number of people will tell you it's half the number of electrons in bonds. If we talk about for carbon, for instance, it normally has 4. There is 2, 4, 6, because each bond has 2 electrons. 8 electrons divided by 2 gives you 4. I personally prefer just to count the number of bonds. It gives you the same number either way, minus 4. Either way works, whatever works for you. Nitrogen, count the number of bonds. 1, 2, 3, 4. And it normally has 5. And here we have our first formal charge. Tells us that it's positive 1. This means that the nitrogen has less electrons than it normally has, so it's acting as a positive molecule in this case, or positive atom, or part of this bond in this case. It's almost like an ion, but not quite. What this tells us is this molecule is inherently unstable. Anything with a formal charge that isn't 0 is inherently unstable, but there are more stable arrangements. We look at the oxygen. Normally there is 6 electrons, but in this case, 1 bond and then 1, 2, 3, 4, 5, 6 electrons in lone pairs gives us a total of 7, gives us a formal charge of minus 1. Now, 2 things you can do to check yourself here. First, does your formal charge add up to the overall charge of the molecule? This is a neutral compound. There's no ion charge on it. So does your formal charge add up to 0? 0 plus 0 plus 1 minus 1 gives you 0. If you had an ion, let's say like carbonate, which has a minus 2 charge, your formal charge should add up to minus 2. Here, it adds up to 0 because we have a neutral molecule. So we have a formal charge of minus 1 on the oxygen, plus 1 on the nitrogen, 0 and 0. Let's take a look at the second drawing. Hydrogen is still 1 and 1. Carbon's normally 4. Nitrogen's normally 5. Oxygen's normally 6. But if we go through and count, in this case, carbon has 1, 2, 3 bonds, and then 1, 2 electrons in lone pairs, which gives it the minus 1 charge. Nitrogen is still 4 bonds, which gives it the plus 1 charge. And oxygen has 2 bonds and 2 lone pairs, so 1, 2, 3, 4, 5, 6 gives us 6, 0. So again, check your charges: 0, minus 1, plus 1, 0. Okay. They told us right off the bat that there would be a formal charge, and we verified it, we've looked at it. Now the question is, why is having the formal charge on the oxygen better than having it on the carbon? That's what this question's ultimately asking. Why is this structure better for formal charge than this one? In this particular case, the top one is better because the electronegativity, or how the electronegativity works out. Whenever there's a formal charge, whenever there's a negative formal charge, the molecule with the highest electronegativity should have the negative charge. Looking at this, look at your periodic table. It goes carbon, nitrogen, oxygen on the periodic table. Oxygen is the furthest to the right, which means it is the most electronegative. Since it's the most electronegative, it should have the formal charge. And if we look at our scoring guidelines, they say in the diagram on the left, the carbon atom has a formal charge of 0 and the oxygen has a formal charge of -1. In the diagram on the right, the carbon has a formal charge of -1 and the oxygen has a formal charge of 0. The diagram on the left is a better representation because it puts the negative formal charge on the oxygen, which is more electronegative than the carbon. Okay? Two things here. One, you get 1 point for getting your formal charges. You get the second point for having the explanation appropriately justified. That is A on to B. 2B then gives us a lot of information. It gives us this chemical reaction that says it can be converted between isocyanic acid and fulminic acid using this reaction here. Notice how the C and N trade spots. It also then gives us the Lewis dot structure for them. And again, notice how the order is different. This is HCNO, this is HNCO. Notice how they swap. And it says, using the information here, we're using the electron dot diagrams of the fulminic acid and the isocyanic acid, shown above, and the table of average bond enthalpies below. Determine the value of delta H for the reaction of HCNO gas to form HNCO gas. Whenever we're talking about delta H, there's many ways you can go about it. You could be talking about the heat of reaction. You could be talking about bond enthalpies. You're talking about delta H formation. In this particular case, we're talking about bond enthalpies, which means our method of solving this is going to be this equation here. Delta H equals the sum, or sigma, of enthalpies of your reactants minus the enthalpies of your products. Most textbooks will say broken and formed. I tend to go reactants and products so you can tell them apart. Basically, the amount of energy it takes to break these bonds minus how much energy is freed up when these bonds are reconstituted tells you what your delta H is. In this case, we look at each of our molecules. First, we have an H and C bond, which is here, which is 413. Then we have a C triple bond with N, which is 891. Then we have an N single bonded to O, which is here. So all these will be added up. That's how much energy it takes to break all those bonds. And then we're going to subtract how much energy is freed up when those bonds are formed. Right off the bat, we have the H to the N. Then we have the N to the C. Double bond. Do make sure you don't get those mixed up. And then we have the C double bonded to the O. 745. Once you've got all those numbers, add and subtract. Make sure you include your parentheses. Double check, make sure all your math works out. If you add this all up, this section here gives you 1505 kilojoule per mole, minus this section here, which gives you 1751 kilojoule per mole. Subtract the two of them, going all the way forward, you get negative 246 kilojoule per mole. Double check your sig figs. All these numbers are 3 sig figs, so you're good. So this would have a negative delta H. This is also worth 2 points. First things first, you should always be formed minus, should always be broken minus formed, or reactants minus products. Getting that set up properly is worth 1 point, and then getting your delta H down here at the bottom is worth the second point. C says a student claims that delta S for the reaction is close to 0. Explain why the student's correct. They don't even tell you, is the student correct or not? No, why are they correct? And this has a star next to it because it will not be on the 2020 AP exam, but it is still good to cover. And entropy is based on disorder, how disorganized, how free to move something is. If you have more of a gas, it's more disorganized. If you have more substances, you can rearrange them differently. It's a lot like socks in that way. If you have more socks, you can have more pairs or mismatches of socks. Secondly, it's based on what type of clothes they are, or type of molecules, if we want to not torture the metaphor, are. In this case, they're both gases. Gases are more free to move. If one was a liquid, it would have a lower entropy. So in this case, we need to look at the number of moles and the state of matter. First things first, state of matter. Gas. They're both gases, so there's no one side that's inherently more free to move, free to be disorganized or chaotic than the other. The second is number of moles. If you have more gas, you have more socks. It's easier to get them mismatched or different possible patterns, but there's the same number of moles. So there's no change in the number of moles, there's no change in the amount of gas, there's no change in the number of moles of gas, there's no change in the states of matter, so therefore the entropy should be close to 0. Answer that, you get another point. A more proper response would be something along the lines of the change from fulminic acid to isocyanic acid is a rearrangement of atoms with no change in phase or number of molecules. Entropy is close to 0. That's C, which would be worth 1 point. On to D. D continues on with the information we found in C. It says which species, fulminic acid, HCNO, or isocyanic acid, which is HNCO, is present in higher concentration equilibrium at 298 degrees K. Justify your answer in terms of thermodynamic favorability and the equilibrium constant. Thermodynamic favorability tells me that you're looking for delta G. Equilibrium constant tells me I'm going to be looking at K. So I need to justify this in terms of delta G and K. So the clear place to start is to find delta G and K. There are a couple equations for delta G, but I know I want to use this one because I found delta H in B, and then C talks about delta S. And that's the only equation that ties those together, and it has this T here. So let's go ahead and plug in some numbers. We said the delta H was negative 246 minus 298. And then S we said was almost 0. Okay. Now this isn't exactly going on, so instead of having an equal sign, it would perhaps be better to have this approximate sign. But because delta S is so small or so close to 0, we can say effectively that delta G here is negative 246 kilojoules per mole. Okay? And since delta G is negative, this tells us that the reaction favors the products. The reaction will proceed forward. It'll go this way. So in terms of thermodynamic favorability, delta G is a negative value, which tells us the products are favored. Halfway done. But it also asks about K. So let's calculate K. The only equation we have that we can have all the numbers for is delta G equals negative RT ln K. We already have delta G, we just found it, or we have an approximation of it. R is a constant, 8.314. T is temperature, 298. All we need to do is rearrange for K. If you want, you can do the math all the way out. If I solve for K, I get K equals E to the delta G over RT. And I can plug in the numbers, but I know delta G is negative. And E to a positive number, which negative times a negative would give me a positive number, tells me that it's going to be greater than 1. If E was 0, it would be exactly 1 and it would be SOL. But because it's a positive times a positive, we're going to get a number that's bigger than 0. Maybe small. We're not exactly sure how much bigger than 0, but still bigger, which tells me that K is going to be greater than 1, and I'm done. If you're not confident in that, just plug in your numbers. K equals E to the negative times negative 246 divided by R, which is 8.314, because we're talking in joules or kilojoules, times 298. Plug it in, solve it out. Plug it in, solve it out, you get this number out. I notice how I converted to joules because 8.314 is in joules, and I get a ridiculously large number. Either way you go about it, if you just go, okay, it's going to be positive because delta G is negative, or you actually plug in the numbers, you'll get K is greater than 1, which tells you the products are favored. So, because K is greater than 1, based on the equilibrium constant, the products are favored. Because delta G is less than 0, in terms of thermodynamic favorability, the products are favored. Answering both gives you 2 points, one for each. D then ends, and then there's an odd split in the question. It says the ammonium salt of isocyanic acid is a product of the decomposition of urea, CONH22, represented below. And you see this decomposition reaction. And then on the next page, it continues on. The student is just studying the decomposition of reaction, runs the reaction at 9 degrees Celsius. The student collects the data on the concentration of urea as a function of time, as shown by the data table in the graph below. And here's your data table, and here's the graph you get. The student proposes that the rate law is rate equals K CONH22. Explain how the data supports the student's proposed rate law. So the student has proposed a first order rate law. How do we know it's first order? Because there's no exponent here, which implies that it's 1. If there's no exponent, it's implied to be 1. Keep that in mind. A first order reaction will have a constant rate of decay. It'll have the same half-life all the way through. So if we come up here, we go, okay, at T0, it was 0.1 concentration. At T10, it's 0.5. At T20, it's 0.2. At T30, it's 0.125. Every 10 hours, the concentration of this halves. So, how we say the data supports this? The concentration of our solution halves every 10 hours constantly, which suggests a first order reaction, thus proposing the rate law we see before us. E part 2 talks about or asks us to, using the proposed rate law and the student's results, determine the value of the rate constant K. Include units with your answer. So the rate law here is a first order rate law. And we know that because there's no exponent, which implies that it's 1, and it's the only term, which tells us that this is a first order rate law. And since this is a first order rate law, we know the equation for this. There's a simple and easy equation for K, which tells us that K equals 0.693 over T 1/2. So now we need to figure out how long it takes to halve. If we can look at our table, we started with a concentration of 0.1. How many hours passed until we halved that concentration? Well, 0 to 10 tells us that it halved in 10 hours. And if we check again, it halved again in another 10. So it's 10 hours. Go ahead, solve that. We're going to K equals 0.069. 2 sig figs because we only rounded to the nearest whole hour. Per hour, -1. Done. If you'd prefer instead, you can rearrange the rate law to get K equals natural log of the initial concentration minus the natural log of the concentration at a time, and then divide by the amount of time it took you to get there. And pick any 2 points. Doesn't matter which ones you pick. Literally any 2 points will give you the same answer out. You could even pick the 0 and the 10. Either way we'll get there. This will, if you plug in any values whatsoever, you'll still get the 0.069 hours. And you're done. On to F. F then goes and adds onto it. It says, so the student learns that the decomposition was run with the solution at a pH of 13. Briefly describe an experiment, including the initial conditions that you would change and the data you would gather to determine whether the rate of the reaction depends on the concentration of OH minus. So you need to describe an experiment where you vary OH to determine its effect on the rate law. So what you would need to do is you need to set up an experiment where everything else is held constant, and then you measure the rate of the reaction based on the differing initial concentrations of OH. So a possible way of going about this would be keeping everything constant, temperature, initial urea concentration, change the initial concentration of hydroxide, or change the initial pH, and measure the rate of reaction change from there on, and compare the two results to see what order reaction it is with respect to hydroxide. That's all you need. You can go more in depth and talk about the exact procedure, but really all you need is a sentence or two. That is 2017 AP Chemistry FRQ 2. Each question, E1, E2, and F, or with 1 point each. Sorry, I couldn't write that on there due to, well, working from the PDF. Thanks. Have a good day.